Hi everyone, I welcome you all to my channel Knowledge Center. So as you all know that I have started the analog electronics, and in the previous session of analog electronics I have given the characteristics of diodes. So in this session now let's discuss about the applications of diodes. The major applications of semiconductor diodes are rectifier. It can be used as a rectifier and it is also used as a clipper and clamper. So these are the three major applications which has to be studied in this analog electronics first chapter. Right. So today I am going to explain you the concept of rectifier. First let us take up one application, that is the rectifier. So as you all know, rectifier is nothing but which converts AC to DC. In general it has been defined as conversion of AC to DC. But practically when you talk, you need to answer it like this. This is going to convert the alternating signal into pulsating DC. So this is the exact answer, because rectifiers will give you a format pulsating DC as an output, not a pure DC output. Because we know DC is nothing but a straight line with the same magnitude for all time duration. But in rectifier we won't get this. Now let's see what we get as an output in a rectifiers. So let's look into that. So for that, I hope you got the definition now. Rectifier is nothing but which converts AC signal into pulsating DC signal. So in this rectifier, again there will be a classification like half wave rectifier and full wave rectifier. So we get two types of rectifiers. So whereas half wave rectifier in the sense, we'll take up that, and even full wave rectifier is nothing but further we can classify in full wave into two parts. In full wave rectifier we get bridge rectifier, and yes, the second one is center tapped rectifier, center tapped transformer rectifier, right? So these are types of rectifiers. Now let's have a look over what actually happens in half wave rectifier, how the circuit has been designed, how it has been made, and what will be the functioning of a full wave rectifier. So to look into that, first let me take the half wave rectifier. So half wave rectifier is nothing but it's going to have only one diode in a circuit, and the output has to be observed. So we take for that, to get output we'll consider one resistor. This consider it as a load, right? Here we get the output. Now what about the input? Input is to be AC, right? So AC is nothing but alternating, so that we use a transformer as an input source. So let us give a transformer. The secondary of transformer is given to the diode. Okay, so here we give a single phase AC supply, right? This will be a half wave rectifier. Now let's see, the input of transformer will be single phase AC, and that will be like this. So this is the input, positive cycle and negative cycle. Let me draw it clearly. I will draw it here. So the input will be positive off cycle and negative off cycle, right? This is one cycle. This is what the input is given to the transformer, right? Then the same input will be taken to the diode. During positive cycle, during this period, we get plus here, we get minus here, right? So this is going to be given to diode, and this is anode of diode, this is cathode. And already told you in the previous session that diode will be conducting only during a condition, and that condition is when anode is at higher potential than the cathode. So for any rectifier, clipper, clamper, the most important thing which you need to concentrate on is to understand when diode is on and when diode is off. Okay, so now if I give a positive here and cathode is connected to negative here, so anode is at higher potential than the cathode, so therefore I can say diode is on. During this session, D on, diode is on. Okay, if it is on, it's nothing but current will flow like this. Current will flow through this, and when current flows here, we get the output voltage. Now we are assuming that this is an ideal diode. There is no loss. Okay. So then let's see what will be the output. For this off duration, we get the same, whatever the input I have, we get the same as the output. So we can represent the same picture. But once it come across this point, here the voltage is in a reverse direction. So the polarity will be changed now. This is going to become minus and this will going to be a plus. So when we have, here we have negative, here we have positive. So it means anode is at lower potential than the cathode. So diode will not conduct now. During this negative off cycle, diode will be off condition. So I can write here D is off. So if this is off, it's just like a open circuit. If it is an open circuit, definitely there is no flow of current. We won't get any current here. The current here is 0. If current is 0, voltage will also be 0. So we won't get any output for this duration. So it will be just a 0. So this is the function of a half-wave rectifier. So we got only half of this signal as an output. That's the reason why it has been termed as an half-wave rectifier. Okay, and this we can call it as a DC, but not the complete standard DC. It is variation is there in the magnitude, right? So it is called as a pulsating DC. It is not the constant. From 0 to pi, 0 to 180 degree, there is some variation. Okay, so it is called pulsating DC. Now let's I hope this is clear for you guys, right? If this is clear, just press the like button there. Now let's move for a full wave rectifier. In that, let's see how the circuit is for full wave rectifiers and what will be the output. You need to observe the things. We had one diode in a half wave rectifier. So when you go for a full wave rectifier, there will be a more number of diodes, right? So let me take the input, that is from transformer, that is an AC input. Then we'll have a diode here. This is almost similar to the half wave, but now let me have one more diode here, right? So I'm having two diodes, D1 and let me name it as D2. Let's say the signal, input signal, this is a half wave input signal. Okay, let me draw the signal here and see how the output will be. So let me give this as an input signal, half wave input signal, and for this signal, now let's see what would be the output. Okay, so let me change the marker. Here the input signal is given for positive off cycle. Let's see what's going to happen. You need to observe this part here. We got a transformer, but the secondary is having one more tapping here. Center of the transformer, secondary winding, we have a tapping. We have taken one connection out of it. That's why it is called center tapped transformer or center tapped full wave rectifier. Okay, so when we give this positive cycle, here we get a plus, here we get minus. So once we get a plus, this diode is going to be on, and here we have a negative at the anode, right? We have negative at the anode. What about this cathode? Say anode is having negative, that's okay. What about the cathode? Cathode, is it connected to any voltage source? No, it's not connected to any voltage source. So it's nothing but here it is going to be 0. Now this is negative, this is 0. So cathode is at higher potential. Therefore, this diode is going to be off, right? So D1 is on, D2 is off. How the current will flow? When this is off, no current will be there in this diode. The current will flow like this and current will be flowing like this. It will come back to this resistor and this is the return path, neutral path, right? This is the ground, right? So that is how you need to understand. There we have branch here, but here because of this is off condition, current in this branch is going to be 0. So we can say that during positive cycle, D1 will conduct and the voltage across R is going to be the same voltage what we have here. So for this off cycle, we get voltage like this, right? Now if I go for second cycle, means for second off cycle, that is the negative cycle. In this reverse cycle, now we get negative here and positive here. So this diode is going to be off because we have the lower potential at the anode compared to the cathode, and this is going to be plus, so this is going to be on. Now there will be no flow of current in this branch, in this loop. We get current here like this. Current will be flowing like this, right? So again we get the voltage drop in this resistance R, right? And there is no polarities for the voltage drop across the R, so we get the same shape of output at this cycle. So we got two pulses. We got two pulses for a complete cycle, right? That's why it is called full wave rectifier. Full wave rectifier, right? And looking into this, we can conclude that full wave rectifier is better than the half wave rectifier, right? Because it is giving better output than the half wave rectifier. In half wave rectifier, we got only half of the output, whereas here we got almost, right? After this, I will also make the comparison of this half wave and full wave rectifier. There will come to know what is the similarities and what are the advantages and disadvantages of both, right? Now let's see one more type of full wave rectifier, that is bridge rectifier. So this is also a full wave rectifier which is used, input is given by the transformer, but here we don't need a center trap transformer. So before going to the bridge type of a rectifier, I just want to tell you one thing, that why should I go for bridge rectifier, right? See, whenever the inventions has been made, we make the inventions only if you have any problems in the present conditions, present circuits. In this circuit, the problem is this center tap transformer. Getting of center tapping from the secondary of a winding of a transformer is difficult, because we want exact difference over there, right? Here, for example, if you give the supply as V maximum Vm, for first half cycle here I should get Vm, for next half cycle for this half portion I should get Vm, right? So getting that center tapping, exact tapping, is a difficult task, and also it increases the weight of that kind of a transformers. So even cost will also increase, right? So that is the drawback we had. So in order to overcome that, we got another kind of a full wave rectifier, that is bridge rectifier. So let's see how to get, without center tapping, how to get a full wave rectifier. So here we use the transformers, but very most important thing we need to concentrate here is we use a transformer without center tapping, but we use a number of diodes. What we use here will be different. So let me show it here. It will be in the form of bridge. It is going to have 4 arms, each arm consisting of a diode. Right? Okay. Right. So this is how the diode is going to be, and you can have a resistance in between like this. This terminal is connected here. So this is how the bridge rectifier looks like. This is how the bridge rectifier looks like. This is the resistance R, where across which we get the output. Now let's analyze this circuit with the input. Say this is the input, AC input. Now let us analyze it. What happens at each off cycle? Right. Okay. Input will be given. Let's assume we have given the positive off cycle. So when we give the positive off cycle, here we have plus, we get minus here. Okay. So say this is D1, D2, D3, D4. Let's name it. Right. When we give plus, here we get positive, here also we get positive. And now tell me, among these two, which diode is going to conduct? Yes, as I told you, anode should have a higher potential. So here positive is higher than the 0. Here nothing is we have means it is going to be 0. Right. So D2 is going to on. D2 will be on. Right. Whereas D1 we have positive at cathode. So this is going to be off condition. Right. So D1 is going to be in off condition. So how the current will flow now? Current will flow like this through this diode. And now we have two branch here. Whether current will flow through this or this, definitely current will be divided. But now D3, look at D3. We have cathode here, right? And we have anode here. Anode is no way connected. It is connected to where? It is connected to negative terminal, and we have positive here. So D3 is also be off. That is going to be in off condition. So current here is going to be 0. So the remaining where the current should flow now. This is the only branch where the current will flow. and voltage drop will be there across the resistance, and that is the same as the input, right? Full maximum voltage will be dropped here, and then it will flow like this. This is positive, so anode is higher potential, it will conduct. So D4 is on, then it will come back like this, it will go to the reverse neutral terminal, right? So this is output we got, and here during positive off cycle, diode D2 and D4 are in on condition, right? Same way it happens in negative cycle. Here negative cycle, what happens? It will be reverse, right? So whichever were off, now those are going to become on. This will be minus, this will be plus. So D4, let's see, this is plus, so D3 is on, D2 will be off, current will flow like this, and it will go to D1. So D1 is on, D4 is off. So current will flow like this, right? So it will come back to neutral. Then again we get a V maximum across this output load R, right? So we got the two pulse in the one cycle. This is as similar as this. Both are same. So both are named as a full wave rectifier, but here we use the bridge format, so it is called bridge rectifier, where we use a center tap transformer, so it is named as a center tap type of a full wave rectifier. I hope it's very clear for you to analyze the circuits. Now let's make some simple comparisons of this half wave, full wave, and in a full wave two types. So let's have the comparisons of these three kind of transformers, rectifiers, sorry. So for half wave rectifiers, I'll just write it as HWR, half wave rectifier. Full wave rectifier, under that center tapped full wave rectifier, and we'll have a bridge type of full wave rectifier, FWR. Okay, so first let me see what are the points to be considered here, and these points are really helpful even in the competitive exams. So that's why I just made some list of comparisons here. So number of diodes, first take, I'll write a point here, HWR, and let me name this as a center tapped full wave rectifier. So here let me make a list of parameters. So list of parameters, number of diodes. So according to the discussion, we can easily say that in half wave rectifier we get only one diode. That is an advantage, number of diodes are less. Here in center tap transformer we had two diodes, that is okay. Whereas in bridge full wave rectifier we had 4 diodes. So when you just look at this point, we can say easily that this is going to be a problem, this is going to be costly, right? But that is not only the one parameter which we need to concentrate, we need to concentrate on other parameters also. Let's see what are those. Average DC current, average DC current. So average current in half wave rectifier, average current in half wave rectifier is going to be, say if this is the signal, this is what we used to get in half wave rectifier for one cycle, right? So we got maximum current here, but under for what is the area? What is the area under that? That is 0 to pi, right? So the total current divided by the area under the current will give you the average. So we can say the formula for that is Im by pi. Im by pi, because only for 0 to pi we have a current. After that we don't have current, right? Whereas for full wave rectifiers we used to get it like this. 2 off pulses we used to get, 0 to 2 pi. For 1 complete cycle you need to consider, right? 0 to 2 pi. Here also I considered 1 complete cycle, but I got output only for half cycle. So Im by pi. Here we got 2 times of Im by pi. Whatever we got here, we got double of it. So I can say that 2 into Im by pi. Average is the maximum current divided by the area under it. So area here is pi, Im and pi, Im by pi. So 2 times we got. So that is the formula, right? And the same for this, because here also we get the same output. So this is advantage. For full wave rectifier we have better average current than the half wave rectifier. Same way we can write for voltage also. Em by pi, 2 Em by pi, 2 Em by pi. Now let's see current, RMS current. So the RMS current, root mean square. Root mean square for full wave rectifier, for sinusoidal output, full wave sinusoidal output is going to be Im by root 2. Even here also we get full output, so we get Im by root 2, right? Means root mean square of a sine wave is 70.7% of right? 70.7%. So I'll just tell you the basic concept here. Root mean square is nothing but what? When we give a DC for any circuit, whatever the heat developed by that circuit in a circuit, means say there is a resistor and I give a DC supply plus minus and I close it. So when I give DC supply of say 5 volt, there will be a flow of current and there will be a heat developed in this I square R, that is the heat developed in the resistor. Now I will remove this and I apply AC supply of same magnitude 5 volt, right? Now we will observe that what is the current, what is the heat developed in that, so I square R. Now that comparison is called a root mean square. So when we apply AC, that effect will not be similar to the DC, because in a DC if I apply 5 volt, that will be constant for all the time duration, right? 5 volt will be constant, so the heat, whatever the heat developed will be higher, larger. Whereas when you go for an AC, it is going to be like this. It's altering. Only at one point we are getting it as 5 volt. At the remaining points it is less than 5. So the effect of this AC is less than the effect of DC. That effective result is called RMS. Okay. So that is what we have written here. So for full wave it is Im by root 2. Whereas for half wave it is Im by 2. You need to remember this point. For half wave it is just 50% of DC. Effect of that is 50%. Whereas here 70.7%. Right. Next, same way we can write it for RMS for voltage. Next, this is important, maximum efficiency. So what would be the maximum efficiency of half-wave rectifier and full-wave rectifiers? See, half-wave rectifier maximum whatever the output we are getting is 50%. Means if I give one cycle, I get output as only half of it, right? So this is only 50% is output what we are getting. But that too 50% when you get, if it is an ideal condition, there is no loss in the diode, there is no loss in resistance, but practically there will be a loss. So the maximum efficiency for half-wave rectifier will be less than 50, that is 40.6%. And for full-wave rectifier we get 2 times of this, because we get 2 pulses, right? So 40.6 plus 40.6, 81.2%. So now comparatively I can say that full-wave rectifier is lot better than this. Its efficiency is higher. That's good, right? Then ripple factor. So ripple factor is most important. Ripple factor is nothing but whatever the pulses we are getting here, output pulses, right? So this, the content of AC in a DC output, that is called ripple factor. The content of AC component in a DC output is called ripple factor. Generally this content should be less, right? But in half-wave rectifier we have very more content of AC in output. So it is 1.21, that is the range. Whereas if you go for a full-wave rectifier, it is 0.482. Here also it is full wave, so 0.482. You can compare this and this table. Everything is same, only with the number of diodes has been variation. There is one more important point which varies here. Let's see that. So ripple factor is okay. Now let's see the peak inverse voltage. Peak inverse voltage. Name indicates that peak inverse in a reverse direction, right? So what would be the reverse direction voltage we can give for the diode without breaking of it? So the maximum reverse voltage which can be given in the half-wave rectifier is Vm, maximum voltage. If it is positive 10 I am giving, negative 10 should be the in a reverse direction. Whereas here in full wave rectifier also it is Vm, but for this it's going to be a 2 Vm. For center tap full wave rectifier, this is going to be 2 times of Vm. So this is the advantage of center tap full wave rectifier, because 2 times of Vm is nothing but we used to have a center tapping transformer at the secondary side. So we get Vm here and Vm here. So Vm plus Vm, 2 Vm. That's why I told here it is 2 Vm, right? 2 Vm is the peak inverse voltage. So in reverse direction I can give up to 2 times of the maximum voltage without breaking the diode. That's the point, right? So that's the advantage of center tap transformer. Then the ripple frequency. Let's see the ripple frequency. Ripple frequency is nothing but ripple frequency has to be whatever the frequency means, number of cycles per second. Frequency is nothing but cycles per second. Okay, so ripple frequency is nothing but whatever the frequency, input frequency we have, that will be the Same for half-wave rectifier, 50 hertz. If input is 50 hertz, out ripple frequency will also be 50 hertz. Okay, but for full wave rectifier, it's going to be double because we have two pulses over there. So it will be doubled, or if it is 50 hertz, then we can say it as a 100 hertz. So I have written this with a reference of input I have given as 50 hertz. Right? In exam they may ask you that what is the ripple frequency of a full wave rectifier if the input frequency is 60 hertz. Then you should write the ripple frequency as 120 hertz. It's a double. Don't fix for 100. Right? So you can just take it as it is as similar as the input frequency in half-wave rectifier. Whereas here double the output frequency, double the input frequency, or 2 times of a input frequency. So these are some of the important points which has to be remembered for competitive exams. So I have given it in a table form. I hope it is very clear for you. If this is helpful, like the video, share among your friends. Thank you.